All right. Did everyone have a good lunch? Okay, no sleeping. I'll keep an eye on you. Have you ever, when you're in a lecture or something and you begin to be sleepy, the best thing to do is find someone else who's falling asleep. Totally keep you awake because it's fun and funny. Anyway, okay. So this afternoon we'll be spending a lot of time going over calibration curves and standards. And there will be a hands-on component to it. So first, you can get this from Panorama, but it should be on your USB under calibration curves. There's a data set called, what is it called? Study 9.1, Site 56B, Agilent 6490. You should be able to find it on your USB drive. And then just unzip it somewhere and have it ready because we'll be going over some of those files. Okay. So there were a lot of questions earlier about standards, and standards are very important. And if you cannot get heavy labeled proteins, which are kind of the ideal, there are a variety of other options you can choose because we can't always get the ideal, unfortunately. So we'll be talking about internal standards versus external standards, protein versus peptides versus global proteome standards like SILAC, or extended peptides, which is the full tryptic sequence plus the native amino acid sequence on either side of the tryptic cleavage point, and then how to use them. So the question goes back to how we quantify and why use standards. So you might remember yesterday I had this equation up. It kind of mimics Beer's law in spectrophotometry, where we have a signal. And this will correlate to a concentration, and there will be some background signal that needs to be accounted for, and then some kind of coefficient. I think the largest effect may be due to ionization in mass spectrometric analysis, and this is highly dependent upon what solvent your sample is in, if there are things co-eluting with it, voltages, the distance between the tip that you're spraying with and the orifice the ions have to go into. There are a lot of things that can affect intensity of your signal that are just very difficult to tease apart. So the idea is you get a standard that you can put into your workflow as early on as possible, and that will go through the same processes as your analyte and likely experience the same ionization, fragmentation, separation by LC, sample preparation, and so on. So when you spike the standard in early on, it will help account for some of the variability because it will be going through the same steps. And so ideally, you'd like to spike it in as soon as you get your sample, before you do any sample preparation. One day, I would love it if when you go to the hospital and they collect your blood in the vacutainers, like the standards be in there. Wouldn't that be awesome? Because then it would just, from step one, as soon as the blood leaves your veins, it goes right in. Who knows if we'll ever get there. So a lot of the sources of variability from the workflow are listed. The auto sampler sometimes doesn't always inject the right thing, or there might be air in your vial in the bottom. The LC separation, sometimes the pumps aren't working properly, and so that can affect reproducibility of retention time, or peak area. Electrospray stability, if you get boogers growing on the tip of your sprayer, then you can sometimes get droplets forming and unstable signal. And detection, if the signal intensity is too low or too high, or if your electron multiplier is beginning to die, then all of these issues will affect your signal. So ideally, when we run a response curve, we want to see how the peak area changes as we change the concentration of the analytes. And ideally, we would love it to be a one-to-one relationship, a y equals x kind of relationship, but that never usually is the case. Here, this was done from a serial dilution, and you can see it doesn't have quite a linear relationship when we plot just the peak area of the analyte. And so this dotted line is a linear regression with the equation shown up there. If we take the same data, those peak area from the analyte, and we normalize it to the internal standard that was in every sample, that's what it looks like. So all the data points, kind of like what happened yesterday with the IRT, everything gets normalized back, and now we have a much better looking linear relationship. A lot of people, I have rants about some aspects of calibration and quantitation, so I don't mean to offend anyone, but there's some things I feel very strongly about. So the R-squared value, the correlation coefficient, is what a lot of people use to describe how like the straightness of a line or how well the points fit on a line. That's there and it's easy to get from Excel because you just click a box and it prints it out. But a better way, in my opinion, is to have a confidence interval so that you have a better idea of how well each particular point fits on the line. And so just saying I have an R-squared of 0.99 doesn't necessarily mean that you've got a straight line with all your points on it. So that was just one thing. All right, so in that previous example, we were using internal standards so that the LC, ionization, fragmentation, detection were all experienced at pretty much the same time between the analyte and the internal standard. It's not always necessary or possible to use an internal standard, and so often external standards are used. And so this kind of just goes through the differences between the two. As I'd mentioned before, internal standards account for variability from the moment you spike them in until the analyte's detected. And this can aid in interference issues in your samples. So if you're analyzing a lot of biological samples and they might have slightly different chemical backgrounds, different matrices. Some might have an interference in your analyte while others may not. And it's not easy to tell if you only look at one transition or if you only compare to an external standard. It's not always straightforward. External standards, so the idea here is you would, much like a BCA assay where you plot response of the spectrophotometric signal against concentration of protein, and then you analyze your sample separately, not with the albumin or whatever the protein standard is. You would generate a response curve and look at the slope and the y-intercept, and then you would take your signal from your analyte, run in a different sample, and plot it on that curve and calculate concentration from that curve. This may aid in interference issues, but again, it depends on the number of transitions monitored. If you only monitor one, then it's not straightforward to tell if it's artificially being inflated or not. So this is why I always choose a minimum of 3 for confidence. And so sample matrix is something that you kind of really need to pay attention to it. Because it strongly affects what goes on in the ionization process in mass spectrometry, as well as the chromatographic process. So here, this is just looking at ideally what we would want to see, which is you see, and this is an example from spectrophotometry again, absorbance versus concentration. You see a straight line, you measure the absorbance, you bring it to the line, you calculate concentration. So we apply similar principles, except with mass spectrometry, we're looking at signal intensity or peak area ratio. So over here is looking at potential things that could go wrong with UV or absorbance detection. And again, the blue is the theoretical calibration curve, and you could get some nonlinearity, right? Now, that may not necessarily be a bad thing if you're looking over very large concentration ranges. That may just be how the peptide behaves. If it behaves that way all the time, then that's okay. I have this thing where I always prefer to see a linear response, and if it's not linear over the whole range, I define the range over which it's linear. So now I know the linear range, and I have more confidence detecting things in that range. But there are other things that can influence this. In mass spectrometry, we could have saturation. There could be interferences that cause the analytes to not fall on that line. And so the idea is you want to characterize your analyte in the sample matrix and potentially in very similar but other sample matrices. So you can look, if you're working with plasma, you can look at pooled plasma, you can look at individual plasma, you can look at horse plasma as potential options to see if there's a chance that anything interferes. Okay. And so working down from internal standards, there are a lot of potential options that you can seek out. I guess going from the bottom up, the easiest ones that are most commonly found these days are these synthetic peptide standards. You can contact, there are a variety of companies that will synthesize peptides of a certain length, even with modifications, and give you a pure form where they might have done amino acid analysis on the solution to determine the concentration. They might give you a multi-spectrum to show like mass spec purity. And they're not terribly expensive. If you purchase the heavy isotopically labeled versions, they will be more, and you can use those as internal standards. If that's out of the price range or for your budget, you can get light ones made and use those as external standards, or you can use the method of standard addition by adding those, Andy mentioned it earlier, into your matrix and seeing the change as you add those in. Extended peptide standards are really similar to synthetic tryptic peptide standards, except, as I mentioned, they include the native amino acid sequence on the either side of the tryptic cleavage points. So the idea there is you have a peptide, you spike it in with the trypsin. You might spike it in during the reduction alkylation process. You spike trypsin in, and then trypsin's going to cleave it down to its fully tryptic sequence, much like your analyte. And the idea is to sort of mimic digestion efficiency of the light peptide that's coming from the endogenous protein. And I have some examples of working with that, and they're not very straightforward, and you often have to do a lot of characterization of your standard. So just word of caution. And then heavy protein standards, these are not always possible, particularly if you work with membrane proteins or proteins that are insoluble or super huge, or they can't be expressed. So if you have the option to use them, they get you much closer to accurate measurements, but it's not always possible. And then SILAC, if you're growing, or similarly like O18 labeled proteomes, if you're able to get your sample matrix are very similar and then isotopically label it, either if you're growing cells in culture or if you're doing this O18 labeling, then kind of everything in the proteome will be very similar to what you're trying to monitor for your analyte. And we'll go through the process. So potential options. Another option is a labeled reference peptide, and this is something that was explored as an option to not have a heavy peptide for every single peptide in your method. And the idea here is you have one or maybe a couple of heavy peptides that you spike in that are not the same as things in your sample, so they won't have a same mass to charge and mess up any other measurements. And you normalize the peak area to these labeled reference peptides. These, for example, if you spiked IRT type peptides into your sample, those could be used as labeled reference peptides. Right, and so they could be spiked in at the digestion point or after desalt, depending on what variability you'd like to account for. And not as expensive as heavy peptides for individual analytes. And so this is a slide I showed yesterday, but it looks at how using internal standards affects the variability, or how the variability is affected by these internal standards. So the coefficient of variation over measurements of the entire response curve are very small when you normalize every peptide to its individual internal standard. And then as you back away and add less specific internal standards, the coefficient of variation grows. And this CV is basically the variability of your entire workflow, because it's accounted for in some ways in these two steps, but that is your absolute variability from start to finish. So synthetic peptides can be easily synthesized. Now, these days, heavy amino acids can be incorporated anywhere along the peptide backbone. Conventionally, lysines and arginines are labeled because we usually follow the Y ion series, so the Y product ions will be different between light and heavy fragments. They're reasonably inexpensive. You can spend $500 and get enough peptide to last your lifetime, pretty much, unless you spill it like I do. And yeah, so the downside is they don't account for variability from the reduction alkylation step, unless you spike those in during that step, or maybe the desalt or not, depending where you add them in your workflow.
For this, just spike it before you do the LCM execution, or you spike it
So usually I would recommend spiking it in as early as possible. So I would evaluate on a per peptide basis, spiking it in during digestion, like with the trypsin, because you need to understand the peptide stability. And so this goes to what Lindsay was talking about, or did you talk about it yet? A little bit. Yeah, stability of your standards can be studied, and you can get information about stability of your analytes from that. So if you put it in with trypsin, but it somehow gets cleaved or modified or falls apart, then you wouldn't want to do that. But you wouldn't account for the variability due to the digestion. So it kind of just depends. You can spike it in anywhere, but you have to be very upfront with what variability you're addressing and what you're ignoring because you're not accounting for it. Okay, so this was an interesting data set. This was from the very first CPTAC study done in the mid-2000s, where we had peptides. So this is the peptide, first 4 amino acids, GYSI, is from the protein CRPC, reactive protein. And these are 3 different experiments, and then the columns are 2 different sites. So the sites analyzed very similar sample kits that were prepared at one site and then distributed. Here in experiment 1, the sample matrix was pre-digested, and then synthetic light and synthetic heavy peptides were spiked in to generate a curve where the heavy peptide was spiked in at a fixed amount and the light peptide was varied according to this concentration. In the second experiment, the proteins, light proteins were available. Those were pre-digested and spiked into pre-digested matrix, so there wouldn't be a matrix effect of digestion of those proteins in the matrix. And then the heavies were spiked in a fixed amount. The proteins were spiked into increasing amounts across the different samples. Everything was measured in triplicate. And then the last experiment was neat plasma, had the light protein spiked in. The denaturation reduction alkylation process occurred, and the heavy peptide standards were spiked in at the end, again with a fixed concentration. And in this case, the protein concentration, again, was supposed to be increasing, much like experiment 2. So these are plotted on a log scale so that we can see what's going on down at the low concentration. But, and this diagonal straight line is the y equals x regression. So what we see here, each different color is a different transition. 3 transitions were monitored per peptide, again in triplicate. What we see is kind of an overestimation when we just are looking at the synthetic peptides spiked into digested sample of how much of the analyte is in there. When the proteins are digested, we're underestimating. We're not getting to that 100% line. And you can rationalize it's probably due to digestion efficiency. Maybe the protein isn't digesting 100% to completion, meaning for every 1 mole of protein, we're not generating 1 mole of peptide. It might be 1 mole of protein to 0.7 or something. And then for this last example where the light proteins were spiked into plasma and then digested altogether, we have practically no recovery of that protein. So this kind of gives you an idea of the effect of the matrix. So the protein was digested along with the matrix here, and we didn't recover it. Versus maybe incomplete digestion efficiency. Or it could be that we just didn't have the proper concentrations of our stocks that we used to do these experiments. So that's always an assumption you have to make about the concentration, is that you think you know what it is. But to be honest, there's really no accurate way of measuring the concentration. Amino acid analysis is the best for proteins. It's okay for peptides, and it has an accuracy of like 30%, so it's not great, but it's what we have. So moving on to digestion, This is a great paper that goes over digestion kinetics for peptides, and some of them are released. So when you digest with trypsin, the ideal situation is that you have an immediate digest and release of peptides and that they stick around forever. And you would want the top one is from the protein and the bottom is the stable isotopically labeled protein. And you want them to have the same curves and exist for the same amount of time, right? The problem is that's not always what happens. And so if you look at the release rate, some proteins or peptides decay in the solution after they're released. Some of them have a steep decay. Some of them have a shallower decay, and they might not have this release and exist response. Ideally, you want your peptide that you're monitoring to have the same behavior as your internal standard, but again, it's not always possible if you're working from synthetic peptide standards. So just another thing to consider. And this is why doing digestion studies, those repeatability studies, is always an important step.
Go maybe one back. On the lower panel in the middle, this concurrent signal for light and heavy seems to be different. If it's such a heavy protein, why is that?
Why what? I missed the first part. They have similar signal, true.
So the kinetics seem to be. Oh, okay, or maybe I'm missing. And the violet is a ratio,
Right.
Oh.
Yeah, so it's the kinetics are similar. You do get that. But that's the point, is you want to make sure that your standard is reacting similarly as your analyte, but it isn't always the case, and so it's best to try to measure it and like map out the relationship so you can see what happens, because it might, like, depending on where you stop the digestion, if they have a different rate, you might be able to stop a reaction, the digestion early and like minimize the decay. So lots of characterization. The more information you get, the more you need, right? It's kind of a pain. So winged peptides were this project that I undertook when I was at the Broad, and it was just really complicated. We had a bunch of light proteins and we had a bunch of heavy synthetic tryptic peptide standards, fully tryptic. And we're like, hey, let's see if we have these winged peptides with the additional amino acids synthesized in super heavy form, so extra heavy amino acids, if we can look at digestion of the light, digestion of the winged peptide, and compare it to this fully synthetic tryptic standard. So the idea here is the digestion variability may be minimized, and that would result in better accuracy if you have an exact concentration of the internal standard. These are harder to synthesize. They're bigger, so they're potentially less soluble. And you can't just take the peptide and infuse it on the mass spectrometer, run MALDI on it, because it's not the tryptic peptide. It won't behave the same way as your analyte. So from that standpoint, they're challenging to work with. And so we were looking at other ways, like how do you know their exact concentration? Again, amino acid analysis is the best. LCUV is possible, but again, do you have to digest it first? How do you know it's digesting to completion if you don't know its initial concentration, and all these details? So they're a bit complicated, which is why we never wrote a paper about it, because we had some inconclusive results. So these are all the proteins that we had light protein forms of. And then these are the tryptic peptides that we had C13 and 15 labeled. Heavy versions of, you could see with the amino acids that are labeled. These in here had internal heavy amino acids, so they're a little different. And then the winged peptides we had synthesized had 6 additional amino acids according to the native protein sequence, primary sequence, before and after. We made some modifications, like this asparagine might have been a glutamine that we were worried that it would cyclize and screw things up, so we had it substituted in the synthesis. And then you can see they're extra heavy labels so that we could differentiate these super heavy ones from these regular heavy ones. Yeah, this is just complicated, but I don't want you guys to fall into the same pit I did. So the other question was, is there an effect of amino acid wing length on the digestion efficiency. So in the previous example, we had 2 peptides per protein, 6 amino acids on either side of the tryptic site. Here we did a smaller number of proteins, 2 peptides per, but we varied the wing length from 2 to 6 on either side of the tryptic cleavage point to see if that had any effect on digestion efficiency. So if we were to pursue this, would we have to add on 6 amino acids, or could we get away with 2, which would be a lot cheaper and easier? Okay, and so for this experiment, we had the light proteins that we spiked into plasma. We had the winged peptides that we call them super heavy. We would digest and then add in the fully tryptic synthetic peptides at the end. And we would use those as a normalization for calculating how much of the winged peptides came out and the light peptides from the proteins. Oh yeah, so then the other thing we wanted to do is characterize when we digest the winged peptides or the light proteins, what do we get? Do we get fully tryptic? Do we get miscleaved? And so we had some additional cleavage products that were present, which you don't see if you don't target for, right? And so this is showing, these are the target tryptic sequences we wanted to see that we had heavy peptides for. These are the forms that we saw from the protein. So if it's in bold, it matches what we would expect. If there's another line and it's not bold, it's usually a miscleaved version of the peptide. So this one starts with glutamate, and that's our tryptic one. This one actually had a miscleavage from 2 amino acids added onto the N-terminal side. This one had an extra one. Also, the idea was whatever you see from the light form that's miscleaved, you're hoping to see in the winged form miscleaved. And so for the most part, we saw some extras. In some cases, we saw agreements, but there were differences there where we're like, huh, what's really going on? So then this is all in here so that you can like contemplate it later. It just adds all the details. But what we did is we looked at, for example, 3 proteins, so troponin T, gamma-synuclein, and annexin A7. And we had 2 peptides for each one. So we spiked the protein based on its starting stock concentration, which we're assuming, the wing peptide, and the heavy C13M15 internal standard were all spiked in at the same amount, like 50 femtomole is what we were to detect at the end. And when we took the protein and the wing peptide and we normalized them to the C13 internal standard, this is the peptide coming from the protein, and this is the winged peptide. You see that we're not, from the protein, we're not getting the same response from each peptide. We're getting twice as much amount of this peptide versus this peptide from the proteins. You're like, oh, that's odd. If we normalize that from the wing peptide, then the ratio of these more approaches 1, which is what we would expect. So the idea here is if we take the signal from the light coming from the protein and normalize it to a synthetic tryptic standard, that is not accounting for digestion variability, and we're actually getting like how much is in the sample. We see twice as much of this peptide as here. If we're normalizing against the winged peptide, which also might be underdigested, that effect is taken into account, and we get more down to a 1-to-1. 1 mole of protein releases 1 mole of peptide, which is more accurate in the sense of what we're trying to get is protein number. It's kind of complicated. Does anyone need help? No? Good. I always get turned around when I try to explain this. And so we saw the same effect for gamma-synuclein when we looked at the response of the 2 peptides normalized to the C13 and 15 synthetic peptide. We don't get a 1-to-1 release of the peptides. We get more of this one than this one. The idea is if we were to choose one of these to quantify on, which one would it be? Probably the one that releases more if it doesn't have interference, but like why don't they agree? It's likely because this one's digested more efficiently. So when we normalize it to the winged peptide, we get more of a 1-to-1, which is what we're looking at. For annexin A7, it actually gets worse. So the way that the winged peptides were being digested compared to the native or the light protein was not exactly the same. And so there was some funny business going on there. And it was disappointing because we didn't really understand why a couple of proteins worked with their winged peptides and another one the winged peptides didn't explain or help with accuracy.
Some conditions, so you use quite aggressive matrix. You use serum, right?
Yeah, plasma.
Did you, plasma. Okay, it's almost
Yeah.
the same. Did you try another matrix? Is it the same behavior?
We did not try another matrix, and it could be completely different behavior.
Yeah,
If
I
there's-
suspect it's because in plasma it has so many proteases.
By the time everything was spiked in, it was fully like what we would do is we would add plasma to urea beads
Okay.
and then add the standards into that.
So completely different.
It should be. I mean, there are, again, a lot of assumptions to be made about the sample and if things are active or not, but yeah. All right. So then when we looked at the effect of wing length, this is just looking at 2 peptides from troponin T. This is the average recovery, where up here is 100%. 100% is not on scale here. And then these are the number of amino acids on either side of the tryptic cleavage points. So when we look at the protein and we normalize to the C13N15 peptide standard, we get the same recovery in each of these samples. So each of these was also a separate sample. We couldn't spike all the winged peptides in together because they would get cleaved down to the same thing. We wouldn't be able to tell them apart. So we had 5 different tubes. The protein was spiked in at a fixed amount on all of them. The winged peptides spiked in at the same amount for all of them. And so you can see the protein recovery is very consistent from sample to sample. So that's good, the digestion worked. But the winged peptide recovery was a lot different. So the question there is, did we spike in the right amount? Did we know the concentration, the accurate concentration of the winged peptide? Is this an effect of not knowing the concentration, or is this truly an effect of digestion due to the amino acid sequence? And that's not something we could really tease apart. But the idea was you would want to get maximum recovery, and so wherever this kind of apex, so at 5 amino acids, might be the proper wing length to mimic good digestion efficiency. And then for this peptide, so you can see there are different sequences and the amino acids wings. This one didn't seem to have as strong effect, other than that 2 amino acid wings had the worst recovery over all of them. Protein recovery was consistent, but for this peptide, anything above 3 seemed to be okay, or maybe we had a more accurate assessment of the stocks of those standards. Yeah.
So wouldn't adding length or amino acids to the length of peptide affect peptide synthesis? Because after a while, you have a really huge peptide.
Yeah.
For synthesis, I guess after trypsin comes back down to it. Run it, it's great, but for synthesis, then it starts becoming. And
Yep.
I guess it would be helpful if you have a small peptide.
Yep.
And like a
That was one of the drawbacks, was the synthesis. Once they get beyond a certain length, the synthesis recovery is not quite as good. You might have more truncations or under-synthesized peptides in the sample, and solubility. So one of the problems here was we had this experiment repeated. 3 different individuals did the experiment, and each person got different results. And then I did it 3 times and got the same results as I did the other time compared to the other people. So we didn't know if it was, at first we didn't know if it was a solubility, these aren't mixing well, sample handling kind of thing. And it was not good to know that 3 different people got completely 3 different results. And it was good to know that you could, a person could repeat with a protocol and get the same results. But this is why this never went anywhere, because we weren't sure how to interpret the data or what the causes were. There could be a couple of effects that were just tangled up. Okay. And heavy protein standard, so this kind of goes without saying that if you can get it, these tends to be the most straightforward, but they are also not perfect. Even if you do wind up getting a heavy labeled protein standard, there's still assumptions and things you need to make, as well as making sure it's properly characterized. So this next one was an experiment where we had someone have a...
I'm just wondering why you say that it works better with AAA proteins and the peptides?
Oh, so amino acid analysis hydrolyzes the sample down to amino acids. And if you have a peptide with 20 amino acids, it only has 20 amino acids to determine the concentration from, whereas a protein might have hundreds or thousands. And so you're getting like more measurement points for every amino acid that you can quantify in the amino acid chromatogram. Do you see what I'm saying? Like, if a peptide has 20 amino acids, you might have 5 histidines and 2. You get a low number of each amino acid, so quantifying might not be as rigorous, particularly if it's not fully hydrolyzed. It should be fully hydrolyzed. But in general, amino acid analysis was developed for protein concentration determination, not for peptides. It might have evolved, and there might be ways where it's like totally accurate, but I still don't think it's totally accurate.
You have less problems with impurities, right? Proteins come from an expression or something. You have way more problems there with amino analysis.
I think it's dependent upon where the protein comes from and how it was handled before amino acid analysis. I mean, I don't think you would just take it, and I think you would want to purify it, right? Because if you're purifying a stock, then you would want to make sure the stock is pure before getting the concentration of it. Otherwise, it's kind of useless information, right? Yeah. Okay, so in this experiment, we had fully N15 incorporated protein standards that were spiked in, and so that's represented by the kind of brown chromatogram. And then the red is the light peptide coming from the protein, and then the blue is the C13 N15 internal standard. So we've got light, heavy, and then N15 is the notation here. If we take the data, one set of experiments that were run where we monitored light, heavy, N15, and we plot normalizing to just that synthetic peptide standard, this is the response we see. Again, this is plotted on a log scale so we can see how things work out down at the bottom end. You can see the signal begins plateauing with greater variability, and that's normal. We notice that these points they're not kind of sticking up to the y equals x line relationship, which is, that happens. But if we try to calculate percent recovery of the light peptide based on the C13 and 15 heavy synthetic peptide, we get about 50% for this one concentration point, which is not so good, but it means that maybe the protein didn't fully digest in the sample. If we take those same data points from the light and we normalize it to the N15 protein standard, the peptide coming from that, and we plot the same data, it's just normalized to a different peptide. Now these points fall much closer to the line. We still see this plateau and the variability increase, so it's not changing that because we're down near the LOD, but the percent recovery we're calculating is much closer to 100. And so this is the kind of effect that using an internal standard spiked in much earlier on has. The more sample processing steps your standard can go through along with your analyte, then the closer and closer you become to accurate. I know the title on this afternoon, like this section, is absolute quantification. And that's another thing I feel very about. I don't like to call it absolute. I know a lot of people do because it implies you get a concentration. You're not saying it's 2-fold more concentrated or 4-fold less concentrated. You're saying, I got 50 femtomoles per microliter in my sample or whatever. Some people think that absolute implies that you can get an intensity and report a concentration, simple as that. And obviously that's not straightforward. All of our quantitation, by definition, is relative to a standard, right? So I always consider it like precise relative quantitation rather than absolute. We can do a lot of debating over beers in a bar about that later. So anyway, another option, if you can't purchase things like synthetically labeled isotopic standards, are these proteome standards. So if you can make SILAC labeled cell lines, or if you can do a heavy water digest and you make a bunch of it, this is something you could always spike in with your sample 1-to-1 and see what you get. The downside of that is you are making your sample potentially more complex because you're not just spiking a peptide in, you're spiking a proteome into it. Okay, so let's just say, oh yeah.
So how about, when you talk about standards, heavy labeled or set of top labeled, could you actually synthesize your peptide and what is the percent efficiency of TMT label? You make it all the standard part of TMT.
Yeah, people do that. I don't know what the labeling efficiency is, but if you have a protein or a bunch of light peptides, you can label them with one form of the TMT label and have those as your standards. As long as you label your sample you're going to analyze them in with another form of the TMT. I know people that do that. I personally haven't. It's potentially a more expensive route because of the cost of TMT, but it does give you the flexibility of getting a heavy peptide, like any heavy peptide. Okay, so what I do once I pick standards is I like to look at its behavior for running a calibration curve. I like to determine how much of the heavy peptide I need to spike in my sample, the concentration range, number of points of the curve, acquire the data, process the data, and usually have to repeat. I always have to repeat. Okay, so one question would be, why run a calibration curve? Why can't I just spike my heavy peptide or my standard in the sample and then just take the peak area ratio, multiply by it, right? The problem is you don't know where the linearity falls off. You don't know the limit of detection. You don't know the limit of quantitation. Some of these can be inferred from looking at the reproducibility of the peak area. If it's better, if it's lower than 20%, then that means you've got reasonably precise measurement. However, you still don't know if it's accurate. So running a curve and plotting to see if it has that y equals x relationship or how far off it is often can give you an idea. And if you determine your concentration by using the curve, by taking the signal or peak area ratio and getting the concentration, that will get you a little bit closer to assumed accuracy than just normalizing to the heavy and multiplying by how much heavy is in there. Okay. Validation is not fun, but if you really want to trust your results, it's always a smart thing to do. I used to work at a biopharmaceutical company, and I worked in a group that would develop methods for like peptide mapping and protein characterization that would be punted over to the group that would do the validation. And they would say it's mind numbing. They would make up solvents and like forget to put the acid modifier in, or they would run the assay with the column backwards and like make mistakes that are humanly possible and see how it affected the outcome. The validation we're talking about is not as rigorous as that for what we're doing, and I don't measure things in people samples. I don't do diagnostic measurements. That's something more along the line of what Andy does, and so he will be much more rigorous than what I am doing. But what I am doing is trying to make sure that my results are as accurate and precise as possible during this evaluation step. So yeah, you want to make sure that you have good quality data and that your method is very reproducible. So we had a study, this was the CPTAC study 9, where again we had a couple of phases where we would measure reproducibility, accuracy, robustness from sample prep, from the instrument performance. We had system suitability in here. And the way these were broken down is we had phase 1, which was the entire method development, characterizing the proteins, looking at miscleaved peptides, looking at the digestion procedure, optimizing the gradient, doing collision energy optimization. That took a long time. And then phase 2, we had these samples centrally prepared where one site had digested, desalted, depleted plasma, and they spiked light peptides in a varying amount and heavy peptides in a static amount over these ranges, and then sent them out to have the calibration curves run to a lot of different sites. Here we had the light protein and the N15 heavy protein spiked into plasma that was not digested, and then generated a response curve with the light peptide where the heavy was fixed. And then those samples were sent to the sites, and the sites did all the sample handling after that. So they did denaturation, reduction, alkylation, and so on. So we wanted to see the effect of sample handling. We wanted to see the analytical variability of looking at something that was already prepared and just had to be analyzed. And so we tried to design it in a couple smart ways. But during the optimization process, one question was, how much heavy do we spike in? These were going to sites that had a variety of different triple quad instruments. Some were quite old, some were the newest models. Newer models, you don't need to spike in as much. Older models, you might have to spike a little more. So how do we come to a happy agreement? We had a couple of sites look at samples that had varying amounts of the heavy peptides spiked into the chemical matrix. And then we picked, I think this one, the 5 femtomole. This is 500 attomole and 1 femtomole, 5 femtomole, and 10 femtomole. We didn't want the spike to be too high because our curve went down to like low attomole amount. So we wouldn't want to spike in 100 femtomole and compare it to 1 attomole because it would probably be not accurate. So we settled on the 5. And then this also gave us the opportunity when we were looking at the light signal, even though nothing was spiked in, did it change with the changing amount of internal standard? Are we having carryover in the signal or residual unlabeled form of that peptide? And so this just helped us to understand if that was happening, which it didn't seem to be. And then the concentration range, we wanted to make sure that we didn't really care how high we went. We didn't want to go too high because it often causes carryover problems. And usually biomarker candidates aren't super interesting. I mean, the ones that are super interesting don't often have huge changes, at least not in the samples we were looking at. So we wanted to concentrate on this lower range and make sure we had a lot of closely spaced points so we could best and most precisely interpolate and calculate the LOD and LOQ. So what we wound up doing, also keeping in mind our rule of thumb was we were assuming we could not quite detect down to 1 attomole of a particular peptide in a microgram of plasma. If we were assuming a protein molecular weight of 50 kilodalton, that would translate to this, which is not an entirely impressive concentration of protein in plasma, but it gave us an idea of what protein kind of markers we would be able to hit without doing anything super special with the sample. So we had, this is the concentration range. We had a blank, always have a blank. You want to measure if you have endogenous in your sample. And then we went from 10 femtomole up to, 10 attomole up to 100 femtomole. Our internal standard peptide was spiked in at 10 femtomole. And then our internal standard protein was spiked in at 25. Anyone have any idea why we put more protein in? What was it? Right, so if the digestion isn't complete, then we would have less recovery and the signal would be lower. So we put in more to make sure that we would be able to see the peptides coming from the protein.
I don't understand this and the fact that, so you spiked in the peptide, also the standard peptide would process it all at the same time, and just spiked in the, out of the peptide run, peptide standard run, I don't know.
Everything was all together. So everything, so in this case, the light and heavy proteins went into the plasma, were digested, reduced alkylated, digested, and then we actually spiked the heavy peptide in. We did 2 separate experiments. In one case, it was spiked in before desalting, and the other was after, so we could understand the effect of desalting if we're losing things during that process. But I think most of them were spiked in before. That's probably what these data are showing. But yeah, everything was all in one box. Right, so we were anticipating this range might be around where our limit of quantitation might be. So that's why there are a bunch of closely spaced concentration points around there. Oh yeah, and then, right, the curves. So again, when you look at it on a linear scale, you can't see anything down here. So when we put it on the log scale, you can see where things begin to fall away from the line. So down below a femtomole is where we were beginning to see things not have a correlative response. So if we look at the limit of detection that was determined across all of those peptides, there were 125 for each of these sites. This is the distribution of the LOD for those peptides for individual sites. What we see is like a pretty similar limit of detection average for these sites with a couple gold star winners, right? So this was one of the newer models of instruments as well as this one. This one was a newer model, but it had a crappy chromatographic front end. All of the peaks were double the width, so that kind of inflated that. This was a new user that hadn't really done nanoflow before, and so we and a lot of these 1, 2, 3 were all the same model instruments, just different individuals ran them. So different instruments, different, same model. But you can see the effect is more than just instrument, it's also capability. So that's LOD normalized to the C13N15 internal standard peptide. When we normalize it to the internal standard protein, it's the same data. Again, we just normalize to a different denominator. What you see is all those LODs pop up a little bit, which implies we're not able to get down to as low limits of detection by using the protein normalization. Part of the reason is because the signal from the heavy protein that was being digested and detected as a peptide wasn't quite as good as that 10 femtomole synthetic tryptic peptide standard. So that actually added to the variability of the measurement. However, it helped us when we looked at accuracy. So we also looked at blinded samples. And again, these are all the individual sites. There were 3 different concentrations. These are the data normalized to the C13N15 standard, and the ranges for the concentration for the 125 peptides measured in each box. So they should be 4, 25, and 75 femtomole per microliter, 4, 25, 75. And you can see that many of them don't fall on the line or not even close. When we take those same data and normalize them to the N15 protein standards, now things are falling right on the line or very close, and the distribution of the concentrations determined is much tighter. So it's becoming more accurate based on normalizing to the protein standard. Yes?
Question. So you always use the same peptides for quantitation, whether you do protein standard or peptide standard, right?
Yes.
So you don't discover any new peptides in the protein
No.
standard?
We didn't. We digested the proteins and could have added in more, but likely they would have been like missed cleavage products that showed up. But yeah, we didn't include any others, although we could have, right? So we wound up having like between 3 and 5 peptides per protein for these experiments. We could have added in more if we wanted to go through and look and then include them in the transition list for the triple quad. But we were kind of on the upper limit of what we could monitor at that point because it was over 1,000 transitions for the 3 peptide form experiment, the N15, C13N15, and light. But definitely if it was something like you were doing DIA, then you could go back and probably pull that information out of the data. Okay, how do you qualify your standard? How do you know its concentration? This is just one of those things that I don't think there's been a really good way to know for sure. I think the idea is if you don't know, at least make it reproducible. So if you're changing from one stock of standard to a new stock of standard because you ran out, always make sure you've got enough of both that you can overlap and make sure the responses are consistent. And if they're not consistent, know how they're different. And just make sure you've got fluidity across your data. How do you know if it's stable in solution or stable in storage? These are all things you need to test. You can't assume that when you spike in a peptide at 10 femtomole in a tube that there will be 10 femtomoles of it in a year or in 2 days, or if you leave it out on the bench. Peptides fall apart. I mean, you don't leave milk out on the counter overnight, right? It gets yucky because of the proteins. Anyway, thank goodness peptides don't smell like that. But so we'll have more examples of stability testing later. But for now, we're going to move on to the Skyline hands-on.